Jingle bells jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. Santa Claus is coming to town.
This is the review for your test on algebraic reasoning. Problem number 1 is taken from SAT test preparation materials. We're asked to compare the area of square ABCD, so the area of this square right here, to the square root of 2. And so we have to start looking at some relationships that we can see, and I think that the most helpful relationship is in this large right triangle down here in the lower left hand corner, because we know that by the Pythagorean theorem the sum of the squares of these two legs will equal the square of this hypotenuse, and if we can find this distance we can start to do some things with that. So using the Pythagorean theorem, let me first just make it clear that I'm talking about this right triangle right here. And so a squared plus b squared equals c squared. A and b, both the legs are the square root of 2, so the square root of 2 squared plus the square root of 2 squared is going to be equal to the hypotenuse squared. Squaring the square root of 2 undoes the square root. They're inverse operations, and so the square root of 2 squared is just 2. And the same thing here. So 2 plus 2 equals c squared. So 4 equals c squared. Then we take the square root of both sides of that equation using property of equality. We get that c is equal to the square root of 4, which is just 2. And so if this distance is 2, we see that line segment AB bisects this hypotenuse. Or if you weren't sure about that, you could look at this isosceles right triangle up here, and you see that obviously all sides of the square are congruent, and since these two legs are congruent, this point A, this vertex A, is at the midpoint of this hypotenuse. And so if the entire hypotenuse is 2, as we've determined here, then each of these is 1. Each side of the square is 1. And if each side of the square is 1, the area of the square is 1, because base times height, or side times side, 1 times 1 is 1. So 1 unit squared for the area. So the quantity in box A is 1, and how does that compare to the square root of 2? Well, if you think about where the square root of 2 lies between perfect squares, it's less than the square root of 4, which is 2, but it's greater than the square root of 1, which is 1. And so it's 1 point something. It's actually 1.414. It goes on forever. It's a irrational number, as we learned. And we could find an estimate, but we really don't need to find an estimate to solve this problem, because it's sufficient just to know that it's greater than 1. So B is greater than A. Problem number 2. Solve the expression below for the values A is -1 and B is 4. So we want to substitute those values. I'm simply rewriting this expression. I'm working vertically. I'm rewriting this expression, but everywhere I see B, I'm going to substitute 4. And everywhere I see A, I'm going to substitute the opposite of 1, -1. And so I have B to the -2nd power, so 4 to the -2nd power, multiplied by the product of A and B, so the product of -1 and 4, divided by -2, plus 4 to the A, and A being -1, so 4 to the -1st power. Now, the way we deal with negative exponent is by using the opposite exponent, but first taking the reciprocal of the base. In this case, the base is 4, so 4 to the -2nd power is equivalent to 1/4 to the +2nd power. Multiplied by, I'm going to do some simplifying inside this, inside parentheses here. -1 multiplied by 4 is -4, divided by -2. Remember, negative multiplied by positive is negative. Plus 4 to the -1st power is just 1/4. It's the reciprocal of the base to the positive exponent, which is to the power of 1, which just means that's 1/4. I'm going to do a little bit of computation on the side here. 1/4 squared is 1/4 multiplied by 1/4, which is 1/16. I do any computation on the side to keep this vertical space clear for simplifying. So now this is 1/16 multiplied by this quotient. Negative 4 divided by negative 2 is 2, because 4 divided by 2 is 2, and a negative divided by a negative is a positive. So 1/16 multiplied by 2 plus 1/4. 1/16 multiplied by 2. You could think of that as 2 over 1 if that's helpful, but you see there's a common factor of 2 here. 2 divided by 2 is 1, 16 divided by 2 is 8. So we get 1 times 1 is 1, over 8 times 1 is 8. 1/8 plus 1/4, and I can express the fourth as eighths. So I have 1/8 plus 2/8. So the final simplified version of this will be 3/8. Problem 3 asks us to simplify each of the expressions below, and so we're using the laws of exponents that we learned. X to the second power to the third power, when you have a power of a power, where you're multiplying those, because that would be the same as, let me expand it just to remind you why this works. I mean, we're cubing x squared, so I have x squared times x squared times x squared, and if I expanded that even more, that would be 6x's, so it would be x to the sixth power. But the easy way to do that is, if you remember the rule, power of a power, you multiply those. So 2 times 3 is 6, so x to the sixth power. Here we have y to the sixth multiplied by y to the eighth. Since these have the same base, y, we can add these exponents. If you imagine, I'm not going to show it, but if you can imagine expanding this, I would have 6y's being multiplied together, multiplied by 8y's being multiplied together. So I just have a total of 14y's. So it's y to the 6th plus 8, or y to the 14th, over y squared. And the rule when you're dividing with the same base is to subtract the exponents. So 14 minus 2 is 12. So y to the 12th would be our final simplified version for this expression. The reason that works is, without me showing actually 14y's, you can imagine if I did, divided by 2y's being multiplied together, 2 of these would cancel out. You'd be factoring out 1 2 times, and you'd be left with, instead of 14y's in the numerator, now 12y's. That's why we subtract those exponents. This last expression just combines some of the things we've done in the prior two expressions. We know a power of a power you multiply. So this is the same as b to the 3 times 4 times 5 multiplied by b squared. And so 3 times 4 is 12, times 5 is 60, so that's b to the 60th multiplied by b to the second, and we just add these exponents if we're multiplying with the same base. So b to the 62nd power would be the simplified version for that expression. The last problem on page 1, the baseball diamond formed by the 3 bases and home plate is a perfect square. The area of the square is 841 yards squared. That may be close to the real area, but I probably took some liberty with that number to make sure it was a perfect square. The area of the square is 841 square yards. Write an algebraic equation that could be used to determine the length of x, the distance between second and third base. Well, if it's a perfect square, if this length is x, then so is this length, and so is this length, and so is this length. All of the sides are x. And so you would find the area by multiplying side by side, or x times x, or x squared. That would equal the area, which is already given to us as 841. That's our equation. And then to solve it, we need to undo this squaring. You undo squaring with the inverse operation, which is the square root. Square root of x squared is just x, so x equals the square root of 841. Now, that's not the type of, I've already sort of revealed that it's a perfect square, but if you didn't know that, you would try to find some perfect squares close to it. One that comes to mind quickly is 900. The square root of 900 is 30, because 30 multiplied by 30 is 900, so it must be something close to that. We might imagine, in fact, if I hadn't revealed that it was a perfect square, we might imagine that, okay, it's close to the square root of 900, so it must be some number close to 30. Maybe it's 28 point something, maybe it's 29 point something, maybe it's 28 or 29, we don't know. But we would want to find the square root, the perfect square less than 900. So taking 29 and figuring out what it would be. 29 squared, 29 multiplied by 29, you get 81, carry the 8, 2 nines is 18, and 8 is 26. Now I'm multiplying by 10, so I start with a 0. 9 multiplied by 2 is 18, carry the 1. 2 twos is 4, and 1 is 5. And when we add these up, we get 5, 6, 7, 8, 841 exactly. So it actually is not an irrational number, since 841 is a perfect square. The side length is 29, so 29, the units were yards squared, so this distance would be one-dimensional. It's a piece of a line, so yards. 29 yards for that distance from second to third base, or between any two bases. Okay, that completes page 1. We'll continue the review on with page 2 on the next video.
Jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. Santa Claus is coming to town.